Okay, this is an example problem about potential energy and force. So in this problem, we're going to model the potential energy of a particular atom that's in a diatomic molecule, like, for example, oxygen. We're going to model it as an expression that is some constant a over x squared minus some constant b over x, where x is the distance between the two atoms. So you could imagine, like, here's one oxygen, and here's the other oxygen, and this is the distance between them, x. And it might be easier for you to think about holding one oxygen atom fixed, and that we're thinking about the other oxygen atom and its position x. But really the potential energy refers to the potential energy held between the two of them. Okay, so given that we have this expression for potential energy as a function of x, we would like to be able to find an expression for the force on this atom as a function of x. We would write that as f of x, right? So we know that the force is the negative derivative du dx. And so we just have to take the derivative of this function above. So we get negative 2a over x cubed plus b over x squared. And we can simplify that to write 2a over x cubed minus b over x squared. Okay. Then we'd like to be able to find the equilibrium distance between the two atoms, so the equilibrium value for x. And by equilibrium, what we mean is that the force is 0. And so we can take the expression for the force above and set that equal to 0 to find the equilibrium value for x. So 2a over, let's call the equilibrium value for x, x naught. So 2a over x naught cubed minus b over x naught squared has to equal 0. And then we just have to solve for x naught. So let's see, this means that 2a over x naught cubed equals b over x naught squared, and we can cancel two of these x naughts with two of these. So we end up getting x naught equals 2a over b with just a little bit of algebra. So that's our equilibrium position. Okay, so part C then asks how much energy would we have to give this atom in order to dissociate it? And so by dissociate, what we mean is that we want the one atom to be able to get infinitely far away from the other atom. And so I'm going to show you what this expression for potential energy looks like. It looks something like this. And so this minimum in the potential energy here, that's the point at which the force equals 0. So that's the equilibrium point. That's what we call x naught. And so this question, part C, what part C is asking is how much energy would we have to give this to get out to x equals infinity? So we have the atom here, and it needs to travel all the way out here. So we would have to give it some kinetic energy to get sort of up out of this valley. So we should note that as x goes to infinity, u of x goes to 0, right? And you can just look back at our expression for u of x. Both of those terms, a over x squared and b over x, are both going to go to 0 as x goes to infinity. So we can set up sort of an initial final energy conservation situation where, let's say our initial situation is the atom sitting here at equilibrium at x naught, and our final situation is way over here at x approaching infinity. And so we can say U initial plus K initial has to equal U final. And if we had some kinetic energy in the final situation, we'd add in K final there. But let's say if we want the minimum amount of energy we would need to get out of this potential well, then we want the case where this K final equals 0. We also just said that U of x equals 0 as x goes to infinity, so this term is also going to be 0. So what we're saying is we need some kinetic energy that's equal to negative U at equilibrium. So K initial has to equal negative U initial, which is negative A over x naught squared minus B over x naught. Going back up and checking that expression for our potential energy, it's A over x squared minus B over x. And that's it. Basically, that's the energy that we need in order to dissociate this atom from its molecule. And you can think of this as kind of being like the escape energy. When we talked about gravity, we talked about escape speed. And this is like the same thing, just with molecules instead of rockets, and some arbitrary form for the potential energy that's sort of complicated rather than our gravitational potential energy.